Our problem number 1 is y double prime minus y prime minus 12y equals to 0. Second order linear homogeneous differential equations with constant coefficients are the equations in the form of ay double prime plus by prime plus cy equals to 0, where a, b, and c are the constant coefficients. So whenever we're solving these kind of equations, first we convert our standard equation into characteristic equation here. So ay double prime interprets as ar squared, by prime turns into br, and cy turns into c. So we obtain here a quadratic function. And we all know how to solve quadratic functions using some techniques. And we obtain three results. We obtain either two distinct roots, repeated roots, or complex roots. If we obtain two distinct roots, the general solution to our differential equation will be c1 times e to the r1t plus c2 times e to the r2t, where r1 and r2 are the two distinct roots. If we obtain repeated roots, then our general solution to our differential equation will be c1 times e to the rt plus c2 times t e to the rt. If we obtain complex roots, our general solution will be for y1 alpha plus beta I. For y2 it's going to be alpha minus beta I, where alpha is the real part of the imaginary number and beta I will be the imaginary part of the complex number. And general solution will be e to the alpha t times c1 cosine of beta t plus c2 times sine of beta t, general solution to our differential equation. Let's solve one problem and see how we are doing. Our problem is this equation. First we convert it into quadratic function. So it's going to be r squared minus r minus 12 equals to 0. Then we're going to solve for r. We can factor this out as r minus 4 times r plus 3. We pick up two numbers that multiplies c term and adds up to b term, one of the techniques trinomial factorization. You can even go for quadratic formula for stop-born equations. Here r is equal to 4 r1 and r2 is equal to -3. Since we have two distinct roots, our general solution to this differential equation will be c1 times e to the 4t plus c2 times e to the -3t. And if you are given initial conditions, you can plug in and solve for c1 and c2. This is just general solution to this differential. Number 2 is y double prime minus 3y prime minus 4y equals to 0. Our first step is to convert into characteristic equation. R squared minus 3r minus 4 equals to 0. Then we're going to solve for this quadratic function. So it's going to be r minus 4 times r plus 1. So two numbers that multiply c term, which is -4, and adds up to b term, which is -3. From here, our r1 will be equal to 4 and r2 will be equal to -1. Our general solution, we know the template from here, c1 times e to the 4t plus c2 times e to the -t. Let's do another one. Y double prime minus 4y equals to 0. We convert this into r squared minus 4 equals to 0. If we add 4 on both sides, we obtain r squared equals to 4. And if we take square root on both sides, we obtain r is equal to plus or minus 2. Whenever you have square root, it goes out as plus or minus. So we have R1 is 2, R2 is negative 2, either or. And our general solution is C1 e to the 2t plus C2 e to the negative 2t. So don't have assumption that this is going to be repeated root and it is positive 2. No, this is plus and minus 2. Another one similar to number 3. This is going to be r squared minus 64 equals to 0. R squared is equal to 64. R is equal to plus or minus square root of 64. R is equal to plus or minus 8. Then our general solution is C1 e to the 8t plus C2 e to the negative 8t. Let's check out this one. 2y double prime minus y prime minus 3y equals to 0. This is going to be 2r squared minus r minus 3 equals to 0. Now we're going to factor out this quadratic function. We can apply AC method of quadratic functions. Multiply a term by c term, you obtain negative 6. And two numbers that multiplies negative 6 is 3 times 2, negative 3 times positive 2. And if you add them up, you obtain middle term, which is negative 1. So this is the correct pair. So r minus 3 times r plus 2. However, our leading coefficient was not 1. So we compensated by dividing everything by the leading coefficient. So if it is not divisible exactly, you multiply by r and leave it like that. And if it is divisible, you divide it. So from here we obtain r is equal to positive 3 over 2. Here you obtain negative 1 if you set it equal to 0 and solve for r. Then our general solution will be C1 e to the 3 over 2t plus C2 times e to the negative t. So you need to be fluent in quadratic functions factoring for solving second order linear homogeneous differential equations with constant coefficients. Let's do this one. 8y double prime minus 10y minus 3y equals to 0. We convert it into characteristic equation. 8r squared minus 10r minus 3 equals to 0. Here we can apply quadratic formula to solve for r1 and r2. Our quadratic function formula is negative b plus or minus square root of b squared minus 4ac all over 2 times a. Here our a term is 8, b term is negative 10, and c term is negative 3. In this case, our negative b will be 10, negative 10, plus or minus negative 10 squared is 100, 4 times, a term is 8, and c term is 3, all over 2 times 8. Inside of the radical sign will be 100 minus 96, which is square root of 4, and we have here 16. Square root of 4 is 2, so 10 plus or minus 2 over 16. Now we can separate this fraction. R1 will be 10 plus 2 over 16, and R2 will be 10 minus 2 over 16. 10 plus 2 over 16 is 12 over 16. If you divide both top and bottom by 4, you obtain 3 over 4. And our R2 is 8 over 16, which is 1/2. So our general equation will be C1 times e to the 3/4 t plus C2 e to the 1/2 t. Number 7 is y double prime plus 9y equals to 0. This converts into characteristic equation as r squared plus 9 equals to 0. If you subtract 9 on both sides, r squared equals to negative 9, And if you take the square root, then r will be equal to plus or minus square root of negative 9. Whenever we have negative under the radical, we obtain imaginary number. So we can express negative 9 as 9 times negative 1. Negative 1 goes outside of radical sign as I. So we have plus or minus I, and square root of 9 is 3, so we have plus or minus 3i. So this is a complex root with the real part is 0. Complex numbers are the numbers in the form of a plus bi, where a is the real part and bi is the imaginary part. In our case, our real part is 0. So we have 0 plus 3i, 0 minus 3i. So in our case, 0 is our alpha and 3 is our beta. Our general solution will be y equals to e to the, instead of alpha we have 0t times c1 cosine of 3t plus c2 sine of 3t. And e to the 0 is 1, so 1 times this will not change, so our general solution is y equals to c1 times cosine of 3t plus c2 times sine of 3t. Number 8 is y double prime is equal to 0. Our characteristic equation is r squared is equal to 0. Then r is equal to plus or minus square root of 0. And both r1 and r2 is equal to 0. This is our repeated roots. So our general equation will be c1 e to the 0t plus c2 t e to the 0t. E to the 0 is 1, so we obtain y equals to c1 plus c2t. And if you would like to solve for c1 and c2, you plug in the initial values given. Number 9 is y double prime plus 2y prime plus 4y equals to 0. Our characteristic equation is r squared plus 2r plus 4 equals to 0. This is perfect square trinomial, so it is r plus 2 times r plus 2. Then our r1 and r2 is equal to negative 2. This is repeated roots. So our general solution is c1 e to the negative 2t plus c2 t e to the negative 2t. So don't forget t here. Let's check out this example. D squared y over dx squared plus 4 dy over dx plus 4y equals to 0. Here, the only difference is notation. So d squared y over dx squared is the second derivative. dy over dx is the first derivative. So we have y double prime plus 4y prime plus 4y equals to 0. And this is r squared plus 4r plus 4 equals to 0. This is nothing but question number 9. So you convert into characteristic equation and solve for r and apply one of those general solution rules. So if you see this notation, then you convert it into y prime notation. So let's check out another examples. So what if you have d squared y over dx squared plus 6dy over dx plus 9y. So you convert this into y double prime plus 6y prime plus 9y equals to 0. Because d squared y over dx squared is the second derivative. This is the first derivative. So the only difference is just notation. and then again you convert it into characteristic equation and then solve. Okay, I think the notation difference is also clear. Let's go ahead and check the initial value problems. In these kind of problems, we also need the derivative of the general solution. So let's derive the derivative of each two distinct roots, repeated roots and complex roots general solution, and then start solving this batch. Our y is equal to c1 e to the r1t plus c2 e to the r2t. We're going to take the derivative of this. So y prime will be equal to c1 is the constant, so derivative of e to the r1t is r1 e to the r1t plus c2 is the constant, and derivative of e to the r2t is r2 times e to the r2t. Now we found the derivative of this. Let's plug this in here. Now let's take the derivative of the repeated roots. So our equation is y equals to c1 e to the rt plus c2 t e to the rt. So y prime is equal to, derivative of this is c1 times r e to the rt plus derivative of this will be the product rule. So t and e to the rt is our two functions, and c2 is the constant that we can pull. So when we apply the product rule, f prime times g plus f times g prime. In our case, our f is t and our g is e to the rt. Then our f prime is derivative of t is 1 with respect to t, and derivative of g will be r e to the rt. Now we can plug this in our product rule. So f prime is 1 times g, which is e to the rt, plus f, which is our t, times g prime, which is r e to the rt. If we rewrite this better and insert here, finally we're going to take the derivative of the complex roots equation. Let us now derive the derivative of complex roots. Our general equation is y equals to e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. We can distribute e to the alpha t into each term before we start. And then we can apply the product rule. Product rule suggests f prime times g plus f times g prime. In our case, our f is e to the alpha t and our g is cosine of beta t from the first term. In the second term, e to the alpha t is our f, sine of beta t is our g. So our y prime will be equal to f prime times g. F prime is the derivative of e to the alpha t, which is alpha e to the alpha t, times g, which is cosine of beta t. C1 is constant, we can pull it here. Plus f times g prime. Our f is e to the alpha t, and g prime is the derivative of cosine of beta t. Derivative of cosine is negative sign, so that makes this sign negative. Negative sine of beta t times beta. Using the chain rule, we need to multiply by the derivative of inside function. So we're done with the first term here now. Now we're going to take the derivative of the orange part. Plus f prime times g. F prime is e to the alpha t times alpha, and g is sine of beta t, and c2 is constant, so we can pull in front, plus f times g prime. Our f is e to the alpha t, and our g prime is the derivative of sine of beta t, which is cosine of beta t, times the inside function's derivative, which is beta. If we rearrange and rewrite it here, this is what we obtain from the derivative of the complex roots. Now we have the derivatives of each general solution, so we can start solving our initial value problems. Our problem is y double prime plus 6y prime plus 5y equals to 0, given y of 0 equals to 0 and y prime of 0 equals to 7 as our initial conditions. Our first step is to start by converting this into characteristic equation. So it's going to be r squared plus 6r plus 5 equals to 0. We can factor out this quadratic as r plus 5, r plus 1. So our r1 will be negative 5 and r2 will be negative 1. We know that our general equation in the two distinct roots equals to y equals to c1 e to the r1t plus c2 e to the r2t. In this equation, we can plug our first initial condition, y of 0 equals to 0. This is our t value, this is our y of t value, which is our y value here. So 0 equals to c1 e to the r1 is negative 5, and our t value is 0, plus c2 e to the r2 value is negative 1, and our t value is 0. E to the 0 is 1, 1 times c2 is c2, e to the 0 is 1, 1 times c1 is c1, so c1 plus c2 equals to 0. This is our first linear equation that we're going to use. Now we need our derivative function, which is c1 times r1 e to the r1t plus c2 times r2 e to the r2t. Our y prime of 0 given as 7. This is our t value, this is our y prime. So 7 equals to c1 times our r1 is negative 5, e to the negative 5. Instead of t, we're going to plug in 0, and c2, our r2 value is negative 1, e to the r2 is negative 1, our t value is 0 from the second initial condition. Now we're going to simplify this. This is e to the 0, which is 1. 1 times negative 1 is negative 1, times c2 is negative c2, and e to the 0 is 1, times negative 5 is negative 5, times c1 is negative 5c1, equals to 7. And this is our second linear equation. Using these two linear equations, we can solve for c1 and c2. C1 and C2 cancels each other. We obtain negative 4C1 equals to 7. And from here, we find C1 as negative 7 over 4. And if we plug this in one of the equations above, we find C2 as positive 7 over 4. Now we have C1, C2, and R1, R2 values. So we can write up our unique solution. Y is equal to C1 times e to the R1t plus C2 e to the R2t. So this is our unique solution. Let's do another initial value problem. Y double prime minus 4y prime plus 4y equals to 0. Y of 0 is given 8 and y prime of 0 is given -2. Our first step is to convert this into characteristic equation and factor this out. So from here, both R1 and R2 equals to 2. This is repeated roots, so our general equation will be C1 e to the RT plus C2 t e to the RT. Let's plug in our first initial condition. This is our t value, this is our y value. So 8 equals to C1 e to the 2 instead of t 0 plus C2 0 times e to the 2 times 0. Here 0 times anything is 0, e to the 0 is 1, so C1 equals to 8. Now we're going to use derivative function. Derivative of repeated roots we derived here. Y prime equals to C1 r e to the RT plus C2 times e to the RT plus TR e to the RT. Let's plug in second initial condition. Y prime of 0 equals to -2. This is our t value, this is our y prime. So -2 equals to, instead of C1, we can write 8 because we know it. And our r is 2, e to the 2 instead of t 0, plus our C2 value is unknown, e to the 2 times 0, plus 0 to e to the 2 times 0. Here again 0 times anything is 0, e to the 0 is 1, 1 times C2 is just C2, e to the 0 is 1, times 16 is just 16, and from this equation we find C2 as -18. Now we have C1, C2, R1 and R2 values, so we can write up our unique solution. Y is equal to C1, which is 8, e to the RT, plus C2, which is -18, t e to the RT. So this is our unique solution for this differential equation with this initial values. Let's do one more example. The problem is y double prime minus 4y plus 9y equals to 0. With the given condition y of 0 equals to 0 and y prime of 0 equals to -8. Our first step is to convert into characteristic equation. We know that this is complex roots because our c term is greater than our b term, so let's apply quadratic function. R1 comma R2 is equal to -b plus or minus square root of b squared minus 4ac all over 2 times a. From this quadratic function, our a term is 1, our b term is -4, and our c term is 9. So this function turns into square root of b squared is -4 squared, which is 16, minus 4 times a times c, all over 2 times 1. From here we obtain 4 plus or minus 16 minus, this is going to be 36 divided by 2. Here we obtain -20, so 4 plus or minus -20 over 2. -20 under the radical is equal to 2 root 5i, and 4 plus or minus 2 root 5i over 2. And if we divide each term by 2, we can simplify this. So it's going to be 2 plus or minus root 5i, r1 and r2. So this is the solution to this quadratic equation. In this equation, 2 is our alpha value and root 5 is our beta value. Now we're going to plug in our first initial condition into general solution equation. Our general solution equation is this, and our y value is 0, t value is 0. Sine of 0 is 0, so this term is gone. Cosine of 0 is 1. 1 times c1 is c1. E to the 0 is 1, so our c1 equals to 0. Now we can go ahead and use the second given condition on the derivative function. Our derivative function is this one. And our initial condition is t value is 0, y prime value is negative 8. So our y prime is negative 8. Because our c1 value is 0 and 0 times anything is 0, so this is totally gone. Now we can work with c2 term. Our alpha value is 2. E to the 2, instead of t we write 0, and sine of 0. Sine of 0 is 0, so this is also gone. We don't need this. Our beta value is root 5, e to the alpha t, cosine of 0, because t is 0. Cosine of 0 is 1, e to the 0 is 1, so we obtain only root 5 here. So we obtain only root 5 times c2. From here, our c2 is equal to negative 8 over root 5. We can rationalize this by multiplying both top and bottom by the square root of 5. So we obtain negative 8 root 5 over 5. So this is our c2 value. Now we know our c1, c2, alpha and beta values, so we can write up our unique solution. Our unique solution will be written on this equation using the values of alpha, beta, and c1, c2. So y equals to e to the alpha t, which is 2t, and this is gone because our c1 value is 0 and our c2 value is negative 8 root 5 over 5 sine of beta t, which is root 5 t. So this is our unique solution. At problem number 14, we're going to show that there is no solution to the boundary value problem. First, we start with characteristic equation. R squared plus 4 equals to 0. And we solve for r here. So take the square root on both sides. So r is equal to plus or minus square root of negative 4. So from here, both r1 and r2 is plus or minus 2i because we have negative value here. This is complex roots, which is 0 plus or minus 2i. In this case, our alpha is 0 and beta is 2. So be careful that given initial values are both y, not one of them is y prime. So these kind of problems that says show there is no solution, show there is infinitely many solution. That is both y or both y prime. So you're going to find the general solution and plug in both and then compare. So let's go ahead and use the complex roots equation because this requires that. So our general solution is y equals to e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. Our first initial condition given is y of 0 equals to 0. So this is 0, and wherever we see t is 0. Our alpha value is also 0 and beta value is 2. Now if we go ahead and solve this, e to the 0 is 1. We have c1, cosine of 0 is 1, and sine of 0 is 0. So here we obtain c1 equals to 0. Now we're going to use same equation, y equals to e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. But this time we're going to plug in second initial condition, y of pi equals to 1. So in this case, our y value is 1 and our t value is pi. So let's start from sine. Sine of 2 pi, our beta value is 2. Sine of 2 pi is 0. On the unit circle, 2 pi and angle 0 is coterminal angles. So one full rotation and we come to the same point. So sine of 0 is equal to sine of 2 pi. So this is going to be 0. Again, cosine of 0 is equal to cosine of 2 pi because they are coterminal angles. So cosine of 2 pi is 1 and c1 is 0 here. 0 times 1 is 0. And this is going to be our alpha is 0. 0 times pi is 0. E to the 0 is 1. And 1 times 0 is 0. So we obtain 1 equals to 0. This is not possible algebraically. So this equation has no solution. So eventually this differential equation has no solution when we plug in given initial values. This is not possible. There is no solution. Let's check another one. Let's check this problem. Here we're going to show that there is no solution for this differential equation. We have y prime plus 25y equals to 0. We convert into characteristic equation and solve for r. And square root of negative 25 is 5i. So r1, r2 is equal to 5i. This is 0 plus or minus 5i because our real part is not existing. So our alpha is 0, our beta is 5. Because we are given both prime, we're going to use the prime function. So these type of problems, pay attention that you're given both either y or either y prime. Our y prime function is y prime equals to c1 times alpha e to the alpha t times cosine of beta t minus beta e alpha t sine of beta t plus c2 alpha e to the alpha t sine of beta t plus beta e to the alpha t cosine of beta t. We're going to use this 2 times, so let me copy and paste this. So we're going to use it first time for our first given initial condition, y prime of 0 equals to 5. So because it is equals to 5, we're going to use y prime 5, and our t value is 0. Our alpha value is also 0. And our beta value is 5. Okay, let's begin with sine, because sine of 0 is 0. So this term is gone. This term is gone. Cosine of 0 is 1. However, alpha is 0, so that destroys this. Alpha is 0, that destroys this. So this term only survives. So this is 1. E to the 0 is 1. Our beta value is 5. That's it. So we have 5c2. So 5 equals to 5c2. From here, c2 equals to 1. We're going to apply second initial value. So y prime of pi equals to 8. So this is 8. And our c2 is 1. Our alpha is 0, so that cancels this term. That cancels this term. And sine of pi is 0, that cancels this term. Cosine of 5 pi is 1, because it's coterminal angle with angle 0. So this is 1. E to the 0 is 1. Our beta value is 5. So here, what is surviving? Here 8 is equal to, let's use c2 as c2. So 8 is equal to c2, 5c2. From here we find c2 as 8 over 5. But from the above, we found c2 as 1. So 1 is not equal to 8 over 5, so this is not possible. So these kind of problems that you're showing either no solution or infinitely many solutions, they are given both same, and you plug in proper equation, either distinct roots, repeated roots, or complex roots, and compare. Let's check another problem. Problem number 16. Here we're going to show that there is a unique solution to the equation that satisfies the boundary conditions y of 0 equals to 2 and y of pi over 2 equals to 0. We're going to show that there is no solution that satisfies y of 0 equals to 2 and y of pi equals to 0. And we're going to show that there are infinitely many solutions to this given initial conditions. So we're going to start with our characteristic equation. R squared plus 1 equals to 0. R squared equals to negative 1. Then R1 and R2 is equal to plus or minus square root of negative 1. And that's going to be I. So our real part is 0. Our imaginary part is 1. So this is our alpha. Our beta is 1. This is complex roots, so we're going to use the complex root general equation. Because our alpha is 0, then our general equation is y equals to c1 cosine of beta t plus c2 sine of beta t. Because e to the 0 is 1, so we can ignore this part because our alpha is 0. Now let's go to first initial condition of part A. Y of 0 equals to 2. So 2 is equal to, wherever we see t, we're going to plug in 0. Sine of 0 is 0, and cosine of 0 is 1, so our c1 is equal to 2. Now we're going to plug in second initial condition to the same equation. Pi over 2 equals to 0. Our equation is y equals to c1 cosine of beta t plus c2 sine of beta t. We said that pi over 2 equals to 0. So we have pi over 2 here, pi over 2 here. Our beta value is 1, so we can ignore this as well. 1 times anything is still same. Let's see on the unit circle, pi over 2 is here. So cosine value here is 0, sine value here is 1. Because cosine value is 0 over there, then this is gone. Sine value is 1, so we're going to have just c2. Then our c2 is equal to 0. Our c1 is 2, our c2 is 0. Then our unique solution is y equals to, we can cancel c2, only 2 cosine of just t. So this is the only solution that satisfies given differential equation. Because c2 is 0, we cancel that. So we're good with part A. Let's go ahead and do part B. On part B, we are given same initial condition, y of 0 equals to 2. From here, remember we found c1, 2. And we're going to check the second initial condition. So y equals to cosine of beta t plus c2 sine of beta t. That's the equation we need to use because this is complex roots. And we are given pi equals to 0. So 0, we're going to plug in here pi. Again, pi is here on the unit circle. And the cosine value here is -1 and the sine value is 0. So this is gone. So this is going to be negative c1. Negative c1 equals to 0, so c1 equals to 0. c1 is equal to 2, that's what we said, and we say c1 is equal to 0. This is not possible at the same time, so there is no solution. Let's go ahead and find condition C. Again, same condition, y of 0 equals to 0. From there, we found c1 as 2. And let's plug in the second condition. Our second condition is y of pi equals to -2. Our equation is y equals to c1 cosine of beta t plus c2 sine of beta t. We're going to plug in here pi. We said that pi of cosine is -1 and pi of sine is 0. So this is gone. So here we obtain negative c1 is equal to -2. Then from here c1 is equal to 2. c1 is equal to 2, c1 is equal to 2. So if we substitute here 2, 2 equals to 2. This is infinitely many solutions. If they are both matching the same value, that means that left side and the right side of the equation equals. So that's infinitely many solutions. So in these type of questions, if you obtain one of the constants 0, so you have two options to obtain. You obtain either unique solution or infinitely many solutions. And if C1 and C1 value or C2 and C2 value is not matching when you plug in the boundary values, then there is no solution. Problem number 17 is the last problem of this group. Let's show that if A, B, and C are positive constants, then all solutions of the homogeneous differential equation ay double prime plus by prime plus cy equals to 0 approach to 0 as t is approaching to infinity. Let's assume that our equation ay double prime plus by prime plus cy equals to 0 has a r squared plus br plus c equal to 0 as our characteristic equation. We are given that a, b, and c are positive constants. We know that when we factor out this quadratic function, we need r something and r something. So because our c term is positive, we need two numbers that multiply c. So we have options positive, positive, or negative, negative. But this pair also have to add up b term. Our b term is also positive, so only two positive numbers add up to b term positive. So we have to have r plus some positive value here and r plus some positive value here. So our roots have to be negative. So r is equal to negative d and our r is equal to negative e. We are 100% sure that our roots r1 and r2 are negative if a, b, and c are positive, because that's the only possible 2 plus numbers gives our positive c value and at the same time positive b value. So from this assumption we can solve this problem. So let's go case by case. On case 1, if r1 is not equal to r2, if the roots are not equal, then we have two distinct roots. Then our general equation is y equals to c1 e to the r1t plus c2 e to the r2t. If we take limit of this equation as t is approaching to infinity, we can see the value of equation. Limit as t is approaching to infinity, c1 e to the r1t plus, we can separate the limits because there is linearity, we know that r2 value and r1 value are negative, and when we plug in infinity we obtain e to the negative infinity here and e to the negative infinity here. Let's go ahead and check the e function. Our e to the x or e to the t is approaching to 0 as we go to negative infinity side. So this limit is approaching to 0 because e to the negative infinity is approaching to 0, and this is also approaching to 0. So our y function is equal to 0 plus 0, which is 0. So as we go to negative infinity, two distinct roots, general equation function is approaching to 0. Let's go to case 2. In our case 2, we assume that our r1 value equals to r2 value. So that's the repeated roots. If it is repeated roots, then we're going to use this equation. And that equation is y equals to c1 e to the rt plus c2 t e to the rt. Again, we know that r is negative value and t is infinity, and e to the negative infinity approach to 0. So this is also approaching to 0. So this value is approaching to 0. Let's go ahead and check case 3. In the case 3, we assume that we obtain our root as alpha plus I beta, which is the complex roots. So our equation will be this equation. And in this equation we have e to the alpha t. And our alpha has to be negative because our roots are negative. So e to the negative infinity is 0, and 0 times everything here also approaches to 0. But you need to rewrite the limit as t is approaching to infinity of e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. So if you show that this is approaching to 0 because e to the negative infinity, that's going to be 0, and 0 times everything here will be equal to 0. So in case 1, case 2, and case 3, ay double prime plus by prime plus cy equals to 0 as t is approaching to infinity. So that's it for this set. We will continue with different batch on question number 18.